There is one experience that every human shares, of every language and culture, the experience of birth. Our recollections of birth are hazy at best. They have the feel and aura, not so much of memories as of mystical transfigurations. It would be astonishing if this profound early experience did not influence our myths and religions, our philosophy, and our science. The birth of a child evokes the mystery of other origins, the beginnings and ends of worlds, infinity and eternity. How did the universe arise? What was around before that? Might there have been no beginning? Could the universe be infinitely old?
Are there boundaries to the cosmos? The current scientific story of the origin of the universe begins with an explosion which made space itself expand. About 15 billion years ago, all the matter and energy that today make up the observable universe were concentrated into a space smaller than the head of a pin. The cosmos blew apart in one inconceivably colossal explosion, the Big Bang. And the stuff of the universe, together with the fabric of space itself, began expanding in all directions as they do today. We can visualize this process with a three-dimensional grid attached to the expanding fabric of space. The early cosmos was everywhere white hot, but as time passed, the radiation expanded and cooled, and in ordinary visible light, space became dark as it is today. But then little pockets of gas began to grow. Tendrils of gossamer clouds formed, colonies of great lumbering, slowly spinning things, steadily brightening, each a kind of beast composed of 100 billion shining points. The largest recognizable structures in the universe had formed. We see them today. We ourselves inhabit some lost corner of one. We call them the galaxies. We inhabit a universe of galaxies. There are unstructured blobs, the irregular galaxies, globular or elliptical galaxies, and the graceful blue arms of spiral galaxies. We've been investigating the galaxies, their origins, evolution, and motions for less than a century. These studies extend our understanding to the farthest reaches of the universe. Our ship of the imagination carries us to that ultimate frontier. We view the cosmos on the grandest of scales. The majesty of the galaxies is revealed by science. There are many different ways in which stars are arrayed into galaxies. When, by chance, the face of a spiral galaxy is turned towards us, we see the spiral arms made luminous by billions of stars. When, in other cases, the edge of a galaxy is towards us, we see the central lanes of gas and dust from which the stars are forming. In barred spirals, a river of star stuff extends through the galactic center, connecting opposite spiral arms. Elliptical galaxies come in giant and dwarf sizes. There are many mysterious galaxies, places where something has gone terribly wrong, where there are explosions and collisions and streamers of gas and stars, bridges between the galaxies. The galaxies look rigid and unmoving, but we see them only for a single frame of the cosmic movie. Their parts are dissipating and reforming on a timescale of hundreds of millions of years. A galaxy is a fluid made of billions of suns all bound together by gravity. These giant galactic forms exist throughout the universe and may be a common source of wonderment and instruction for billions of species of intelligent life. Their evolution is governed everywhere by the same laws of physics. We need a computer to illustrate the collective motion of so many stars, each under the gravitational influence of all the others. A billion years is here compressed into a few seconds. In some cases, spiral arms form all by themselves. In other cases, the close gravitational encounter of two galaxies will draw out spiral arms. But when two nearby galaxies collide, like a bullet through a swarm of bees, the stars hardly collide at all, but the shapes of the galaxies can be severely distorted. A direct collision of two galaxies can last 100 million years and spill the constituent stars careening through intergalactic space. When a dense, compact galaxy runs into a larger one face-on, it can produce one of the loveliest of the rare irregulars, a ring galaxy. Thousands of light years across, a ring galaxy is set against the velvet of intergalactic space. It's a temporary configuration of disrupted stars, a splash in the cosmic pond. Galaxies sometimes blow themselves up. The quasars, probably billions of light years away, may be the colossal explosions of young galaxies. But we're not sure. Quasars are a mystery still. The galaxies reveal a universal order and beauty, but also violence on a scale never before imagined. The universe seems neither benign nor hostile, merely indifferent to the concerns of such creatures as we. Quasars may be monster versions of rapidly rotating pulsars, or due to multiple collisions of millions of stars densely packed in the galactic core, or a chain reaction of supernova explosions in such a core. Some astronomers think a quasar is caused by millions of stars falling into an immense black hole in the core of a galaxy. Something like a black hole, something very massive, very dense, and very small, is ticking and purring away in the cores of nearby galaxies. Even a well-behaved galaxy like the Milky Way has its stirrings and its dances. The stars of the Milky Way move with systematic grace. The sun takes 250 million years to go once around the core. The outer provinces of the galaxy revolve more slowly than the inner regions. As a result, gas and dust pile up in spiral patterns. These places of greater density are where young, hot, bright stars form, the stars which outline the spiral arms. These hot stars shine for only 10 million years or so, and then blow up. But as the stars which outline a spiral arm burn out, new young stars are formed from the debris just behind them, and the spiral pattern persists. The sun, marked here with a circle, has been in and out of spiral arms often in the 20 times it has gone around the Milky Way. In this epoch, we live at the edge of a spiral arm. We've looked at internal galactic motion on a small scale across 1 million light years or less. But the motion of the galaxies themselves across billions of light years is different. That motion is a relic of the Big Bang. The key to cosmology, the study of the entire universe, turns out to be a commonplace of nature, an experience of everyday life. Imagine a moving object sending out waves. It could be light waves, it could be sound waves, it could be any kind of wave. When that moving object passes us, we sense a change in pitch. That's called the Doppler effect. If you're the engineer in the cab, then the pitch of your locomotive whistle always sounds the same to you. That's because you're moving along with the source of the sound. But if you're standing alongside the track when the train passes, you hear that familiar shift in pitch, the Doppler shift. The reason this happens is easy to understand once you visualize the waves. A stationary train sends out sound waves in perfect circles like the ripples on a pond. Let's start the train again. Now, the waves spreading out ahead of it get squashed together, and those spreading out behind it get stretched apart. The compressed waves have a higher frequency or pitch than the stretched out waves. The same thing is true for light waves. Color is to light precisely what pitch is to sound. Compressed light waves are made bluer, they're blue shifted. Stretched out light waves are made redder, they're red shifted. At the speed of a train, you can sense the change of pitch for sound, but not for light. The train is traveling about 1,000,000 times too slow for that. It turns out that the Doppler effect for light waves is the key to the cosmos. The evidence for this was gathered unexpectedly by a former mule team driver who never went beyond the 8th grade. During the second decade of this century, the world's largest telescope was being assembled on Mount Wilson, overlooking what were then the clear skies of Los Angeles. Large pieces of the telescope had to be hauled to the top of the mountain, a job for mule teams. One of the drivers was a young man named Milton Humison, the ne'er-do-well son of a California banker. But he was bright and naturally curious about the equipment he had carted up Mount Wilson, and after the telescope was completed in 1917, he managed to stay on here as janitor and electrician. One evening, so the story goes, the observatory's night assistant was ill and Humison was asked to fill in. Humison was a gambling man, celebrated for his skill at poker and at the pool table, but his touch with the telescope was admired even more. He discovered he had a natural talent for using astronomical instruments. He became the virtuoso of the 100-inch telescope. In this instrument, the light from distant galaxies is focused on a glass photographic plate by a great encased mirror 100 inches across. By the late 1920s, Humison was making observations himself.
Mr. Nelson?
Humison, by now, had his own night assistant to help him with the observations.
Afternoon, Mr. Nelson.
Good afternoon, Mr. Humison.
We'll start at 6. I'll be making a spectrogram at the Castle focus.
Yes, sir.
The telescope must be able to point with high accuracy to a designated region of the sky and to keep on pointing there. A machine weighing about 75 tons, as massive as a locomotive, must move with a precision greater than that of the finest pocket watch. Everything must be checked thoroughly. The electrical power system must work flawlessly. Hours before observations are to begin, the dome is opened to allow the temperature inside and outside to be equalized. Humason prepared the sensitive photographic emulsions sheathed in their metal holders to capture with the giant telescope the faint light from remote galaxies. This was part of a systematic program which Humason and his mentor, the astronomer Edwin Hubble, were pursuing to measure the Doppler shift of the light from the most distant galaxies then known. But the most distant galaxies are very faint. That's why, even with the largest telescope in the world, it was necessary to take very long time exposures, often lasting the whole night, and sometimes requiring several successive nights. Humason would give the night assistant the celestial coordinates of the target galaxy. Through the long, cold night, he would have to make fine adjustments so the telescope would precisely track the target galaxy. The galaxy itself was much too faint to see through the great telescope, although it could be recorded photographically with a long time exposure. So the telescope would be pointed at a nearby bright star and then offset to a featureless patch of sky from which, over the long night, the light from the unseen galaxy would slowly accumulate. The telescope focused the faint white light from the galaxy into the spectrometer, where it was spread out into its rainbow of constituent colors. The spectrum would be recorded on the little glass plates.
All right, would you clamp in the drive and salute the focus star, please?
Are you clear? I'm going to salute to the east.
Yes, I think I'm clear. Just take it easy. All right, I have it. Now let's go to NGC 7619. I'm clear. Going to do a 10-hour exposure. What time is it?
7:15.
All right, lights out, please. Dark slide is open.
A large telescope views only a tiny patch of sky. As the Earth turns, a guide star or a galaxy would drift out of the telescope's field of view in only a few minutes. Humason had to stay awake, tracking the galaxy while elaborate machinery moved the telescope slowly in the opposite direction to compensate for the Earth's rotation. The telescope is a kind of clock.
How's the dome?
You're clear.
This work was difficult, routine, tedious. But although they didn't yet know it, Hubble and Humason were meticulously accumulating the evidence for the Big Bang. They had found that the more distant the galaxy, the more its spectrum of colors was shifted to the red.
All right, clear the telescope. I'm coming down now.
If this redshift were due to the Doppler effect, the distant galaxies must be running away from us. At the end of his vigil, Humason would retrieve the tiny galactic spectrum and carefully carry it down to be developed.
Thank you, Mr. Nelson. I'm going to the dark room now. Good day.
Good day, sir.
Humason found a redshift in almost every galaxy he examined, like the Doppler shift in the sound of a receding locomotive. And the farther away from us they were, the faster they were receding. Tied to the fabric of space, the outward rushing galaxies were tracing the expansion of the universe itself. An awesome conclusion had been captured on these tiny glass slides. Humason and Hubble had discovered the Big Bang. At top and bottom are calibration lines that Humason had earlier photographed. In the middle is the spectrum of a relatively nearby galaxy. Every element has a characteristic spectral fingerprint, a set of frequencies where light is absorbed. Prominent here are two dark lines in the violet due to calcium in the atmospheres of the hundreds of billions of stars that constitute this galaxy. Nearby galaxies show very little Doppler shift. But when he recorded the spectrum of a fainter and more distant galaxy, he found the same telltale pair of lines, but shifted farther right toward the red. And when he examined a remote galaxy 4 billion light years away, he found that the lines were redshifted even more. This galaxy must be receding at 200 million kilometers an hour. The painstaking observations of Milton Humason, astronomer and former mule team driver, established the expansion of the universe. In discussing the large-scale structure of the cosmos, astronomers sometimes say that space is curved, or that the universe is finite but unbounded. Whatever are they talking about? Let's imagine that we are perfectly flat. I mean absolutely flat, and that we live, appropriately enough, in a Flatland, a land designed and named by Edwina Abbotta, a Shakespearean scholar who lived in Victorian England. Everybody in Flatland is, of course, exceptionally flat. We have squares, circles, triangles, and we all scurry about, and we can go into our houses and do our flat business. Now, we have width and length, but no height at all. Now, these little cutouts have some little height, but let's ignore that. Let's imagine that these are absolutely flat. That being the case, we know, us Flatlanders, about left-right, and we know about forward-back, but we have never heard of up-down. Let us imagine that into Flatland, hovering above it, comes a strange three-dimensional creature which, oddly enough, looks like an apple. And the three-dimensional creature sees an attractive, congenial-looking square, watches it enter its house, and decides in a gesture of interdimensional amity to say hello. "Hello," says the three-dimensional creature. "How are you? I am a visitor from the third dimension." Well, the poor square looks around his closed house, sees no one there, and what's more, has witnessed a greeting coming from his insides, a voice from within. He surely is getting a little worried about his sanity. The three-dimensional creature is unhappy about being considered a psychological aberration, and so he descends to actually enter Flatland. Now, a three-dimensional creature exists in Flatland only partially. Only a plane, a cross-section through him can be seen. So when the three-dimensional creature first reaches Flatland, it's only the points of contact which can be seen, and we'll represent that by stamping the apple in this ink pad and placing that image in Flatland. And as the apple were to descend through, slither by Flatland, we would progressively see higher and higher slices, which we can represent by cutting the apple. So the square, as time goes on, sees a set of objects mysteriously appear from nowhere and inside a closed room and change their shape dramatically. His only conclusion could be that he's gone bonkers. Well, the apple might be a little annoyed at this conclusion, and so, not such a friendly gesture from dimension to dimension, makes a contact with the square from below and sends our flat creature fluttering and spinning above Flatland. At first, the square has no idea what's happening. He's terribly confused. This is utterly outside his experience. But after a while, he comes to realize that he is seeing inside closed rooms in Flatland. He is looking inside his fellow flat creatures. He is seeing Flatland from a perspective no one has ever seen it before to his knowledge. Getting into another dimension provides as an incidental benefit a kind of X-ray vision. Now our flat creature slowly descends to the surface, and his friends rush up to see him. From their point of view, he has mysteriously appeared from nowhere. He hasn't walked from somewhere else. He's come from some other place. They say, "For heaven's sake, what's happened to you?" And the poor square has to say, "Well, I was in some other mystic dimension called up." And they will pat him on his side and comfort him, or else they'll ask, "Well, show us, where is that third dimension? Point to it." And the poor square will be unable to comply. But maybe more interesting is the other direction in dimensionality. What about the fourth dimension? Now, to approach that, let's consider a cube. We can imagine a cube in the following way. You take a line segment and move it at right angles to itself in equal length. That makes a square. Move that square in equal length at right angles to itself, and you have a cube. Now, this cube, we understand, casts a shadow. And that shadow we recognize. It's, ordinarily drawn in third grade classrooms as two squares with their vertices connected. Now, if we look at the shadow of a three-dimensional object in two dimensions, we see that, in this case, not all the lines appear equal. Not all the angles are right angles. The three-dimensional object has not been perfectly represented in its projection in two dimensions, but that's part of the cost of losing a dimension in the projection. Now, let's take this three-dimensional cube and project it, carry it through a fourth physical dimension. Not that way, not that way, not that way, but at right angles to those three directions. I can't show you what direction that is, but imagine that there is a fourth physical dimension. In that case, we would generate a four-dimensional hypercube, which is also called a tesseract. I cannot show you a tesseract because I and you are trapped in three dimensions. But what I can show you is the shadow in three dimensions of a four-dimensional hypercube or tesseract. This is it. And you can see it's two nested cubes, all the vertices connected by lines. And now the real tesseract in four dimensions would have all the lines of equal length and all the angles right angles. That's not what we see here, but that's the penalty of projection. So you see, while we cannot imagine the world of four dimensions, we can certainly think about it perfectly well. Now, imagine a universe just like Flatland, truly two-dimensional, and entirely flat in every direction, but with one exception. Unbeknownst to the inhabitants, their two-dimensional universe is curved into a third physical dimension, maybe into a sphere, but at any rate, into something entirely outside their experience. Locally, their universe still looks flat enough, but if one of them, much smaller and flatter than me, takes a very long walk along what seems to be a straight line, he would uncover a great mystery. Suppose he marked his starting point here and set off to explore his universe. He never turns around, and he never reaches an edge. He doesn't know that his apparently flat universe is actually curved into an enormous sphere. He doesn't sense that he's walking around a globe. Why should his space be curved? Because there's so much matter in this universe that it gravitationally warps space, closing it back on itself into a sphere. But our Flatlander doesn't know this. After a long while, you'll find he somehow returns to his starting point. There must be a third dimension. Our Flatlander couldn't imagine a third dimension, but he could sure deduce it. Now, increase all the dimensions in this story by 1, and you have something like the situation which many cosmologists think may actually apply to us. We are three-dimensional creatures trapped in 3 dimensions. We imagine our universe to be flat in 3 dimensions, but maybe it's curved into a 4th. We can talk about a 4th physical dimension, but we can't experience it. No one can point to the 4th dimension. I mean, there's left, right, and there's forward, back, there's up, down, and there's some other directions simultaneously at right angles to those familiar 3 dimensions. Now, imagine this universe is expanding. If we blow it up like a 4-dimensional balloon, what happens? An astronomer in a given galaxy thinks all the other galaxies are running away from him. The more distant the galaxy, the faster it seems to be moving. This is just what Humason and Hubble found. On the surface of this curved universe, there is no boundary or center. The universe can be both finite and unbounded. The redshift of the distant galaxies seemed to imply to Humason's contemporaries that we were at the center of an expanding universe, that our place in space was somehow privileged. But if the universe is expanding, whether or not it's curved into a 4th dimension, observers on every galaxy will see precisely the same thing. All the galaxies rushing away from them as if they had made some dreadful intergalactic social blunder. If there's enough matter to close the universe gravitationally, then it's wrapped in on itself like a sphere. If there isn't enough matter to close the cosmos, then our universe has an open shape extending forever in all directions. This saddle universe is only one of an infinite number of possible kinds of open universes. Unlike such closed universes as the sphere, open universes have in them an infinite amount of space. If our universe is in fact closed off, then nothing can get out, not matter, not light. We would then be living inside a black hole. There is one possible way out, though, a hypothetical tunnel or wormhole through the next higher dimension, a place sucking in matter and light. Can we find such a wormhole? Could we survive the trip? We might emerge in some other place and time, perhaps in another universe, or perhaps somewhere else in our own. If you want to know what it's like inside a black hole, look around. But we don't yet know whether the universe is open or closed. More than that, there are a few astronomers who doubt that the redshift of distant galaxies is due to the Doppler effect, who are skeptical about the expanding universe and the Big Bang. Perhaps our descendants will regard our present ignorance with as much sympathy as we feel to the ancients for not knowing whether the Earth went around the sun. If the general picture, however, of a Big Bang followed by an expanding universe is correct, what happened before that? Was the universe devoid of all matter and then the matter suddenly somehow created? How did that happen? In many cultures, the customary answer is that a god or gods created the universe out of nothing. But if we wish to pursue this question courageously, we must, of course, ask the next question. Where did God come from? If we decide that this is an unanswerable question, why not save a step and
conclude that the origin of the universe is an unanswerable question. Or, if we say that God always existed, why not save a step and conclude that the universe always existed, that there's no need for a creation, it was always here? These are not easy questions. Cosmology brings us face to face with the deepest mysteries, with questions that were once treated only in religion and myth.
Who knows for certain? Who shall here declare it? Whence was it born? Whence came creation? The gods are later than this world's formation. Who then can know the origins of the world? None knows whence creation arose, or whether he has or has not made it, he who surveys it from the lofty skies. Only he knows, or perhaps he knows not. These words are 3,500 years old. They're taken from the Rig Veda, a collection of early Sanskrit hymns. The most sophisticated ancient cosmological ideas came from Asia, and particularly from India. Here, there's a tradition of skeptical questioning and unself-conscious humility before the great cosmic mysteries. Amidst the routine of daily life, in, say, the harvesting and winnowing of grain, people all over the world have wondered, where did the universe come from? Asking this question is a hallmark of our species. There's a natural tendency to understand the origin of the cosmos in familiar biological terms, the mating of cosmic deities, or the hatching of a cosmic egg, or maybe the intonation of some magic phrase. The Big Bang is our modern scientific creation myth. It comes from the same human need to solve the cosmological riddle. Most cultures imagined the world to be only a few hundred human generations old. Hardly anyone guessed that the cosmos might be far older, but the ancient Hindus did. They, like every other society, noted and calibrated the cycles in nature. The rising and setting of the sun and stars, the phases of the moon, the passing of the seasons. All over South India, an age-old ceremony takes place every January, a rejoicing in the generosity of nature in the annual harvesting of the crops. Every January, nature provides the rice to celebrate Pongal. Even the draft animals are given a day off and garlanded with flowers. Colorful designs are painted on the ground to attract harmony and good fortune for the coming year. Pongal, a simple porridge, a mixture of rice and sweet milk, symbolizes the harvest, the return of the seasons. However, this is not merely a harvest festival. It has ties to an elegant and much deeper cosmological tradition. The Pongal festival is a rejoicing in the fact that there are cycles in nature. But how could such cycles come about unless the gods will them? And if there are cycles in the years of humans, might there not be cycles in the eons of the gods? The Hindu religion is the only one of the world's great faiths dedicated to the idea that the cosmos itself undergoes an immense, indeed an infinite, number of deaths and rebirths. It is the only religion in which the timescales correspond, no doubt by accident, to those of modern scientific cosmology. Its cycles run from our ordinary day and night to a day and night of Brahma, 8.64 billion years long, longer than the age of the Earth or the Sun, and about half the time since the Big Bang. And there are much longer timescales still. There is the deep and appealing notion that the universe is but the dream of the God, who, after 100 Brahma years, dissolves himself into a dreamless sleep, and the universe dissolves with him, until, after another Brahma century, he stirs, recomposes himself, and begins again to dream the great cosmic lotus dream. Meanwhile, elsewhere, there are an infinite number of other universes, each with its own God, dreaming the cosmic dream. These great ideas are tempered by another, perhaps still greater. It is said that men may not be the dreams of the gods, but rather that the gods are the dreams of men. In India, there are many gods, and each god has many manifestations. These Chola bronzes cast in the 11th century include several different incarnations of the god Shiva, seen here at his wedding. The most elegant and sublime of these bronzes is a representation of the creation of the universe at the beginning of each cosmic cycle, a motif known as the cosmic dance of Shiva. The god has 4 hands. In the upper right hand is a drum whose sound is the sound of creation. In the upper left hand is a tongue of flame, a reminder that the universe, now newly created, will, billions of years from now, be utterly destroyed. Creation, destruction. These profound and lovely ideas are central to ancient Hindu beliefs, as exemplified in this Chola temple at Dharasuram. They are a kind of premonition of modern astronomical ideas. Without doubt, the universe has been expanding since the Big Bang, but it is by no means clear that it will continue to expand forever. If there is less than a certain amount of matter in the universe, then the mutual gravitation of the receding galaxies will be insufficient to stop the expansion, and the universe will run away forever. But if there is more matter than we can see, hidden away in black holes, say, or in hot but invisible gas between the galaxies, then the universe holds together and partakes of a very Indian succession of cycles, expansion followed by contraction, cosmos upon cosmos, universes without end. If we live in such an oscillating universe, then the Big Bang is not the creation of the cosmos, but merely the end of the previous cycle, the destruction of the last incarnation of the cosmos. Neither of these modern cosmologies may be altogether to our liking. In one cosmology, the universe is created somehow from nothing 15 to 20 billion years ago and expands forever, the galaxies mutually receding until the last one disappears over our cosmic horizon. Then the galactic astronomers are out of business. The stars cool and die, matter itself decays, and the universe becomes a thin, cold haze of elementary particles. In the other, the oscillating universe, the cosmos has no beginning and no end, and we are in the midst of an infinite cycle of cosmic deaths and rebirths, with no information trickling through the cusps of the oscillation. Nothing of the galaxies, stars, planets, life forms, civilizations evolved in the previous incarnation of the universe trickles through the cusp, flitters past the Big Bang to be known in our universe. The death of the universe in either cosmology may seem a little depressing, but we may take some solace in the timescales involved. These events will take tens of billions of years or more. Human beings, or our descendants, whoever they might be, can do a great deal of good in tens of billions of years before the cosmos dies. If the universe truly oscillates, if the modern scientific version of the old Hindu cosmology is valid, then still stranger questions arise. Some scientists think that when redshift is followed by blue shift, causality will be inverted and effects will precede causes. First, the ripples spread out from a point on the water's surface. Then I throw the stone into the pond. Some scientists wonder, in an oscillating universe, about what happens at the cusps, at the transition from contraction to expansion. Some think that the laws of nature are then randomly reshuffled, that the kinds of physics and chemistry we have in this universe represent only one of an infinite range of possible natural laws. It is easy to see that only a very restricted range of laws of nature are consistent with galaxies and stars, planets, life, and intelligence. If the laws of nature are randomly reshuffled at the cusps, then it is only the most extraordinary coincidence that the cosmic slot machine has this time come up with a universe consistent with us. Do we live in a universe which expands forever, or in one where there is a nested set of infinite cycles? There's a way to find out the answer to that question, not by mysticism, but through science, by making an accurate census of the total amount of matter in the universe, or by seeing to the very edge of the cosmos. Radio telescopes are able to detect distant quasars billions of light years away, expanding with the fabric of space. By looking far out into space, we are also looking far back into time, back toward the horizon of the universe, back toward the epoch of the Big Bang. Radio telescopes have even detected the cosmic background radiation, the fires of the Big Bang, cooled and redshifted, faintly echoing down the corridors of time.
This is the Very Large Array, a collection of 17 separate radio telescopes, all working collectively in a remote region of New Mexico. Modern radio telescopes are exquisitely sensitive. A distant quasar is so faint that its received radiation by some such telescope amounts to maybe a quadrillionth of a watt. In fact, this is a reasonably stunning piece of information. The total amount of energy ever received by all the radio telescopes on the planet Earth is less than the energy of a single snowflake striking the ground. In detecting the cosmic background radiation, in counting quasars, in searching for intelligent signals from space, radio astronomers are dealing with amounts of energy which are barely there at all.
These radio telescopes, rising like giant flowers from the New Mexico desert, are monuments to human ingenuity. The faint radio waves are collected, focused, assembled, and amplified, and then converted into pictures of nebulae, galaxies, and quasars. If you had eyes that worked in radio light, they'd probably be bigger than wagon wheels, and this is the universe you'd see. An elliptical galaxy, for example, leaving behind it a long wake glowing in radio waves. Radio waves reveal a universe of quasars, interacting galaxies, titanic explosions. Every time we use another kind of light to view the cosmos, we open a new door of perception. As the murmurs from the edge of the cosmos slowly accumulate, our understanding grows. This is an exploration of the ancient and the invisible, a continuing human inquiry into the grand cosmological questions.
Another important recent finding was made by X-ray observatories in Earth orbit. Artificial satellites launched to view the sky, not in ordinary visible light, not in radio waves, but in X-ray light. There seems to be an immense cloud of extremely hot hydrogen glowing in X-rays between some galaxies. Now, if this amount of intergalactic matter were typical of all clusters of galaxies, then there may be just enough matter to close the cosmos and to trap us forever in an oscillating universe.
If the cosmos is closed, there's a strange, haunting, evocative possibility, one of the most exquisite conjectures in science or religion. It's entirely undemonstrated, it may never be proved, but it's stirring. Our entire universe, to the furthest galaxy, we are told, is no more than a closed electron in a far grander universe we can never see. And that universe is only an elementary particle in another still greater universe, and so on forever. Also, every electron in our universe, it is claimed, is an entire miniature cosmos containing galaxies and stars and life and electrons. Every one of those electrons contains a still smaller universe, an infinite regression, up and down. Every human generation has asked about the origin and fate of the cosmos. Ours is the first generation with a real chance of finding some of the answers. One way or another, we are poised at the edge of forever. Except for planetary exploration, the study of galaxies and cosmology, what this episode was about, have undergone the greatest advances since Cosmos was first broadcast. For one thing, at last we have a good photograph of our own Milky Way galaxy, about 100,000 light years across. Here it is. It was taken by NASA's COBE satellite. We see it edge on, of course, since we're embedded in the plane of the galaxy. But you don't need a spacecraft to see it. If it's a clear night tonight, why not go out and take a look at the Milky Way? There's also new evidence suggesting that the Milky Way is not so much an ordinary spiral galaxy as a barred spiral, like this. Important work has now been done on mapping how the galaxies are scattered through intergalactic space. To the surprise of a lot of scientists, on a scale of hundreds of millions of light years, the galaxies turn out not to be strewn at random or concentrated in clusters of galaxies, but instead strung out along odd, irregular surfaces, like this. Every dot in this computer animation is a galaxy. The computer lets us look at this distribution of galaxies from many points of view, but this is how it looks from the Earth. There's an odd mannequin shape that is presented by the distribution of galaxies. This work has been done mainly by Margaret Geller with her collaborator John Huckra at Harvard University and the Smithsonian Institution. It's a little like soap bubbles in a bathtub or in dishwashing detergent. The galaxies are on the surfaces of the bubbles. The insides of the bubbles seem to have almost no galaxies in them at all. An average bubble is about 100 million light years across. And that means that we've mapped still only a very small volume of the accessible universe, the galaxies nearest to us. But pretty soon, we should be able to extend this search out to enormous distances, out to distances so far away in space that we're looking back to the time that galaxies and their structures were first forming. And this poses a real problem. Most cosmologists hold that the galaxies arise from a pre-existing lumpiness in the early universe, with little lumps growing into galaxies. But the background radiation from the Big Bang that fills all of space has now been carefully measured by that same COBE satellite that took that picture. Now, those radio waves seem almost perfectly uniform across the sky, as if the Big Bang weren't lumpy or granular at all. But if the early radiation and matter in the universe weren't lumpy, how could individual galaxies form? How could the bubbles form? Is there a contradiction between the uniformity of the Big Bang radio waves and the bubble structures formed by the galaxies? That's the question. When our survey of the galaxies reaches out to billions of light years, we'll have the answer to this question. Incidentally, maybe you're thinking that the bubbles imply a bubble maker. But then I'd have to ask you, who made the bubble maker? There's another infinite regress lurking here. And to one of the grandest questions, whether there's enough matter in the universe to close it, the only fair answer is that we still don't know. If it is closed, what is the hidden matter that's closing it? Is it faint stars, black holes, massive neutrinos, some exotic kind of dark matter unknown on Earth?
We don't know, but there are reasons to think that we'll soon find out the answers.